Hi, the question we are solving belongs to test series 1 and it belongs to network theory subject in specific to sinusoidal steady state analysis. The question is numbered 5. As per the question, there is a AC circuit given which contains a resistor RL in series with a 5 millihenry inductor, and this combination is in parallel with a series combination of resistor RC and a capacitor of capacitance 150 microfarad. It is given that RL equal to RC and the circuit needs to be resonant for all frequencies, say for all angular frequencies. We have to find RC satisfying these two conditions. We have to find RC satisfying these two conditions. So let us mark the input terminals as A and B. So if the circuit needs to be under resonance, the impedance as seen from terminals, let it be ZAB. So if ZAB is the impedance as seen from terminals AB, if the circuit is under resonance, imaginary part of ZAB is equal to 0. It means that we have to find ZAB, which is the impedance as seen from terminals A and B, and we have to equate the imaginary part to 0 to find RC. So let us find ZAB first. So ZAB is equal to RL plus J omega L in parallel with RC minus J by omega C. Here L is equal to 5 millihenry and C is equal to 150 microfarad. So ZAB can be written as RL plus J omega L multiplied by RC minus J by omega C divided by RL plus RC plus J times omega L minus 1 by omega C. This can be simplified as RL RC plus 1 by C plus J into omega L RC minus RL by omega C divided by RL plus RC plus J times omega L minus 1 by omega C. On rationalizing, this becomes RL RC plus 1 by L by C, sorry, this should be L by C plus J times omega L RC minus RL by omega C divided by, so you have to multiply this quantity by RL plus RC minus J times omega L minus 1 by omega C divided by RL plus RC minus J times omega L minus 1 by omega C. So we can write that as J times omega L minus 1 by omega C divided by RL plus RC whole square plus omega L minus 1 by omega C whole square. So as discussed before, for the circuit to be under resonance, imaginary part of ZAB is equal to 0. So that can be written as minus RL RC plus L by C multiplied by omega L minus 1 by omega C plus RL plus RC multiplied by omega L RC minus RL by omega C equal to 0. It can be further simplified as minus RL RC times omega L plus RL RC multiplied by 1 by omega C minus omega L square by C plus L by omega C square plus omega L times RL RC plus omega L RC square minus RL square by omega C minus RL RC by omega C. So this should be equal to 0, and we see that these two quantities can be cancelled. Similarly, these two quantities can be cancelled. So on simplifying, this becomes omega L times RC square minus L by C plus 1 by omega C times L by C minus RL square. The condition is that circuit needs to be resonant at all frequencies. It means that this term should be 0 and this term should be 0. So further to happen, RL square should be equal to L by C and RC square should be equal to L by C. It means that for circuit to be under resonance, RL equal to RC equal to square root of L by C. On substituting the quantities given, it can be obtained that RL equal to RC equal to square root of 5 into 10 power minus 3 divided by 150 into 10 power minus 6. So, on simplifying, this becomes square root of 1000 divided by 30. So which is square root of 33.333. So the correct answer would be 5.7735 ohms. So the correct option is A.